So, hello, good morning. My name is Bern Wölfel from Wölfel Engineering. Can you see my screen now?
Yes, we can see it.
Perfect. Yes. Hello from Hamburg. We are a traditional German family company that is a specialist in dynamics and mechanics and monitoring. As I said, I'm here in Hamburg and responsible for our monitoring business. And today's topic I would like to talk to is on tower monitoring. Main reason is increased safety and extended lifetime due to an early detection of tower and foundation damage. Yes. Our expertise lies in the field of structure health monitoring. So we just heard from Mr. Reinke the condition monitoring, CMS, and we are specialized in the structure monitoring. So we look into the structures of tower, foundation, and blade, and there we focus on. We have over 2,000 systems, mainly in Europe, installed for the monitoring of tower, foundation, and blades. So damage to a tower and foundation comprises safety. When we monitor such a structure, we focus on vibration behavior that is mostly measured on the top of the tower or inside the nacelle. And secondly, we focus on a static inclination of the tower and foundation structure. Besides those measured data, we analyze also the turbine data that are coming on out of the SCADA system to contextualize the results to the operational state of the turbine. And this analysis gives a long-term trend, a lifetime consumption, and of course, any deviation or damages within the tower foundation structure can be detected. So first, I would like to talk a little bit on the dynamic anomalies of a tower structure. So we select the different eigenmodes during the state of the turbine. So we take the vibrations, we classify them by the turbine data, environmental and operational data. Then we have here the different global frequencies that we detect on each turbine structure individual. And then we normalize this by the key performance indicators to define each individual alarms for each turbine. This is not only possible to detect damages in the tower. There are a lot of damages that occur in the foundation. So what we have seen in the past is a lot of damaging by decoupling of the foundation of the tower, or cracks in the concrete, concrete towers and concrete foundations, and also loosened foundation elements. So typical failures are flex failures based on too strong ULS loads, or we have even seen pull-out failures based on ULS or fatigue loads, shear failures within the foundation or tower structure, and bearing failures, especially in grouted connections in the concrete. For monitoring of these failures, besides the vibration, the tilt, so the inclination of the whole structure is important. Here are two examples. So for flexure failure that comes with certain deformation limits that are related to bending moments, can define this in our model. And then if this measured data are above certain limits, then alarm can be triggered. And this is the same with the shear of failure. So what very important is that you correlate the measured data with your operation data. So important are the wind turbine state data, so power, pitch, but also wind data, temperature. And this measured data have to be compensated to this environmental conditions. One example you see here is a compensation of temperature influence to the measured data. So you have a large variety of measured data, and you want to know if you are in all of your conditions of the turbine, so with strong winds, with less winds, and even if the turbine is at idle, you want to see if you are within the alarm range. So this blue circle has the alarm range, and this red spots are here the measured data. But imagine a strong wind would lead to a very strong deviation, and less wind would lead to almost non-deviations of either inclination or vibration data. And you want to filter out if this is still in the range due to or compensated to the turbine state. And therefore, you need to use artificial intelligence algorithms that give you in all conditions of the turbine the true static inclination. And here you see that if you compensate these dots to the environmental and operational conditions, you can even filter out that depending on the state of the turbine, that only a few spots are outside of the alarm ranges. Secondly, besides the detection of the damages, the consumption of the lifetime based on the damage equivalent loads. So you have design loads. Your turbine structure is designed for 20, 25, or 30 years with certain design loads. So on each conditions that the turbine sees at its life, a certain load is induced into the tower and foundation structure. And if you start in the beginning of the lifetime to measure those loads, and to integrate them in a kind of numerical model, then you can compare every day, every year, if the turbine has seen similar loads than were expected in the design. And after operation of 2 or 3 years, you have a good picture at that special location if this design loads are the same than the real loads. And by that, you can then predict that your turbine has seen much less design loads than the design was anticipated. And thereby you can extend the lifetime of your turbine. Or if your turbine have seen much more loads, then you can predict the damage, an early damage that is coming before the end of lifetime, and can do the respective maintenance measures. So the decision of a further operation after the 20 or 25 years can be taken much earlier than the 20 years are reached, and measures can be taken also much earlier. To sum this monitoring approach up, we have on the one side the monitoring based on inclination and vibration data that can come from any sensor that is implemented within the factory, within the construction of the turbine. very important is that the system gets a connection to the SCADA, and then software can run on one side, acquire the acceleration data, then the inclination data and the turbine state data, and bring this together. And by use of one side, the numerical model that is implemented in the software, and on the other side, on machine learning algorithms, the enhance of the failure detection can be sharpened, and very early on alarming in case of exceeding of certain limits can be triggered and can be put back into the SCADA systems. So the advantages are that you have a combined monitoring to supervise inclination vibration to get a better picture of the structural integrity, that you detect individual into your wind farm the damages of certain structures that are induced to different loads, and you record right from the beginning your fatigue loads, and can do individual lifetime assessment of all your structures within the wind farm. And then if you look ahead in the future, then many of those turbines can run longer than expected in the design phase.
Okay, thank you, Bernd.
Yes, if you have any questions, we can come to this later on.